Hello students, in this video we are going to look at complex eigenvalues. If you recall, so far the eigenvalues that we've been looking at have all been real numbers. But the truth is, eigenvalues are roots of polynomials. And as far as polynomials goes, you are not always guaranteed that the roots are going to be a real number. If you take an example, let A be equal to 0 minus 1, 1, 0. Now, for this matrix A, if we are to find its characteristic polynomial, so if we do determinant of A minus lambda I is equal to 0, here we are going to get lambda squared plus 1, which is equal to 0. Now, the solutions of this is going to be lambda is equal to 1, I, and then a negative I. Now, in cases like this, we say that A has complex eigenvalues. Now, when A, what does it necessarily mean to be for A to have complex eigenvalues and complex eigenvectors? If that, what are they going to look like? So here, let's assume that AX is equal to lambda x, where x is an eigenvector and then lambda is an eigenvalue. So here we are saying that x is an eigenvector corresponding to lambda. Now, because we are in the complex plane, let's go ahead and then find the conjugate, the complex conjugate of AX is equal to lambda x. Now, on the left hand side, here we have A times x, the conjugate of x equal to, and here, and the conjugate of A. Here, similarly, we are going to have lambda times the conjugate of x. Now, because all the terms of A are always real, we have the complex conjugate of A is just going to be A. And we are going to have lambda bar equal to lambda conjugate times S conjugate. So here, what this implies is that lambda x bar is also an eigenvector of A corresponding to the conjugate of lambda. Therefore, we conclude that if lambda is an eigenvalue, then the complex conjugate lambda bar is also an eigenvalue. Now, similarly, if lambda, if x is an eigenvector, then the complex conjugate S bar is also an eigenvector. Now, the process that we use to find the eigenvalues and eigenvectors in the complex plane is the same method as we've been using in the previous section. Now, one thing that we learned in the previous section was also similarity. So here, what will similarity even look like? And we have this theorem to help us see what it's going to look like. So if if we let A be a 2 by 2 matrix with complex eigenvalue, lambda is equal to A minus BI, and its associated eigenvector is V, or both of which are in complex numbers, then we can write A to be similar to some matrix C. And that matrix C is going to look like this. And the P that we use to derive such matrix is given by the first column is going to be the real entries of V, and the second column is going to be the imaginary entries of V. Let's take an example. So let's say, if I have my matrix A, which is equal to 0.5, negative 0.6, 0.75, and 1.1. And with eigenvalues, lambda is equal to 0.8 minus 0.6 I, with and the corresponding eigenvector is -2 minus 4i, and then 5. According to this theorem, if I am interested in finding a matrix which is going to be similar to A, I can have my P. So according to theorem, P A is similar to, here my P, here my C is going to be A minus B, BA, where this is my A and then this is my B. Therefore, my C is going to be 0.8, negative 0.6, 0.6, and then 0.8, with my P, which is equal to real of V and then imaginary side of V. Now with my, I used X for my notation of the eigenvector, so I need to use X over here. Now with my X, the real side of X is going to be the 2 and 5. So here, this is going to be -2, 5, -4, and then 0. So check. When you multiply, check, is C really equal to P inverse A P?